Hi, everyone. Welcome to today's Learn and Share. We are very excited to have today Kaihan Fang from Nanyang Technological University, who is going to present his work, RAMenPaSTA. Kaihan has worked on a while on cryptography. He's done a few papers on multi-party computation and code-based cryptography. We are really happy to have you here today. Thanks a lot for joining us. And the floor is yours.
Okay, so hi everyone, my name is Kaihan Tang and I am currently working as a research fellow in NTU Singapore. So today we present RAMenPaSTA. It's the parallelizable scalable transparent argument of knowledge for RAM. And this work is in the joint work with Minh Phạm in Origin Networks and Nam Ngô. Okay, so this is the outline of my talk. First, I will talk about the motivation and the contribution of my work. And then next, I will talk something about the preliminary, especially for homomorphic complement scheme. And then I will discuss our new definition about conditional folding scheme, including its syntax and security requirement. And then after this new introduction of conditional folding scheme, we construct a generic construction of conditional folding scheme. So for short, I call it CF scheme. And after this generic construction of CF scheme, we construct RAMenPaSTA. This is the short name of parallelizable scalable transparent arguments of knowledge for RAM. Okay, so now I start the first part of my talk about motivations and contributions. Okay, so the motivation is we would like to construct a zero knowledge group for RAM. So for RAM in short, it's a sequence of computation steps with a memory supported. And the aim is to construct a generic and unified framework for verifiable RAM. So it should achieve the following property. The first one is highly parallelizable. So in this case, when proceeding in an iterative group, we can reduce the proving time and the verifier time. And in some case, it may reduce the proving time about sublinear comparing to the size of the RAM. So and because our work is try to construct a generic construction, so we can instantiate our construction in different assumption and group techniques. And here we try to move our construction outside the concept of zkSNARK, including SNARK and zkSNARK. And our works try to leverage just minimal assumption, including the homomorphism of complement scheme. And in this case, we first try to fold everything into a single step. So for example, so the RAM is a sequence of steps like this, and until last step. So we try to fold everything into a small instant. So in this process, the folding process just leverages the homomorphism of complement scheme, and therefore at the final step we just rule at the end. And this is the motivation of Nova. And the final thing is that because our construction is generic, so we achieve the plug and play paradigms. It means that when running our protocol, we can plug anything suitable with our protocol, such as the homomorphic complement scheme and the zero knowledge groups into the construction. Okay, so related work, I list a few related works to our works. So before that, two recent works. This is must proof. The first work is must proof, and the second work is Sublime. They are the two works closely related to RAM. And however, their construction is not generic because they instantiate their protocol in some check arguments, and it should be based on algebraic group model. In short, we call it AGM. And the other works, this is the first one from the other works for IT max. We can call it designated variable designated verifiable zero knowledge. And the second two works the construction are generic. However, in the construction, you need to prove every step of the construction of the proof. I mean, every step of the RAM from step 1 to up to step n. So you need to prove every step. So so here we provide a different approach. We try to prove everything into a small proof, a small instance, and then at this step I will make the proof. So this way we follow Nova paradigms. We follow Nova. Okay, so from this one, okay, so from this one, because we try to move out the context of Nova folding scheme and zkSNARK, then we face a few difficulties. The first one is that when we try to move out the context of Nova, it means we try to avoid the recursion heuristic. It means we try to avoid realizing the random oracle model as a circuit, and in that way, in Nova, for example, in Nova, they fold the two instance into a new instance here. So this folding step incurs that there is no connection between the two instances. If you fold the default instance has no connection. It means it does not imply any connection between the two folded instance. However, in RAM, because you try to fold an n-step RAM like this up to the end, then between every two steps there must be some condition between them. So therefore, the folded instance here must be found successfully if this condition holds. So this is the reason. Regarding this condition, for example, the input and output must match. Input, output match. In some other situation, like the access to memory, also have some connection between the two instances. So therefore, we propose the new construction, the new notion, conditional folding scheme, and then in this notion, it allows us to fold two instances with some condition between them into a new one. And the second one is a generic construction of our conditional folding scheme. In this one, we try to leverage the homomorphism of commitments. Homomorphism of commitments. And after this generic construction, we try to adapt it to make it a zero proof for RAM. And in this way, we can use RAMenPaSTA like what we already introduced. Okay. So now I move to the next level of stop. So this is a preliminary for my talk. It's also called the background. So in this one, I need to use the notion of homomorphic commitment scheme. So in a homomorphic commitment scheme, there is a tuple including pre-algorithms, set up, commit, and verify. So the setup algorithm here, when you run it with some security parameter 1 to the lambda, it returns a commitment key CK. And this is the setup algorithm. So with this CK, so I assume that the CK is implicit in the commit algorithm. So the commit algorithm here receives two things. The first thing is the message, and the second thing is the randomness, and it returns a commitment C. So from this commitment C here, we can verify whether C is a correct commitment of a message and the randomness by running the verify algorithm to return 0 and 1. So 1 means C is the valid opening of M and R. So basic commitment scheme must satisfy two properties. The first one is the hiding property. This means that the hiding property is that we can think like we put the message C, the message M into a box and it returns C. So this box protects the message inside the box. So C here completely hide the message M. This means the privacy of M is not leaked from the public. And the second property is binding. This means that when you commit the message M here, you cannot change M to M prime. So that the verification algorithm still must. This means that you cannot change M to M prime, or more specifically from MR to M prime, R prime, such that verify M prime, R prime, and C is still satisfied. This means you cannot do that. Okay, so here we have additional property of commitment scheme. We call it the homomorphism or homomorphic property. So usually we only require the linear homomorphic property. This means that we have the following things. First, if we have the commitment C to some message M and R, then when you multiply the commitment C by alpha, you multiply the randomness by alpha and multiply M by alpha. This one still satisfied. This means it's still satisfied. And the second thing is that if you have the two valid commitment scheme, for example, C is a valid commitment scheme to M with randomness R, and C1 is a valid commitment to M1 and R1. Then when you take addition of them, M0 plus M1, R0 plus R1, and C0 plus C1, then the algorithm also return 1. So here, because everything usually they go together. For example, we have a commitment C is the commitment of M with randomness R. So everything usually to go together. So we use this notion to represent a commitment tuple. This means when we write this, we understand that there is a commitment C together with some message M, with a message M here, and the randomness R such that the verification of C MR here is satisfied. So this tuple will write like this. It just to imply that M is committed. So in such a way, then when we write alpha times M here, so we understand that the message alpha times M here is committed. And when we take addition M0 plus M1, then we understand that the message M0 plus M1 is committed. And additionally, I need to use some additional protocol. It means the commitment protocol that on a message M, the two parties, for example, prover and verifier. So in this case, the prover commit the message M and send the command C to verifier. So here C is committed by M and R. So it means that the prover sample R by himself and then commit to M with R and return C, and then the prover sends C to the verifier. So verifier here we assume that he keeps the command C, and the prover keeps C, M, and R. Okay, so this is whatever I would like to use in my talk for commitment scheme. So next, so now I start to discuss the conditional folding scheme, our new proposed folding scheme in our result, RAMenPaSTA. So in this conditional folding scheme, so as previously I said, we have two instances. For example, C0. For example, we have two instances C0, W0 satisfy relation R, and Z1, W1 satisfy relation R. So we would like to fold them into a new instance here, C and W that also satisfy a relation R here. So in such a case, we require that the condition between Z0 and Z1 must satisfy by having this relation R condition. This means that there is some connection between Z0, Z1 with respect to the witness W0, W1, and some auxiliary witness W prime here, such that when folding together, not only these two things satisfy, but this one also satisfy. Then if this one satisfy relation R, it means if the folding instant here belong to R, then the reverse here also satisfy that the first instant belong to R, the second instant belong to R, and the condition between them satisfies. Okay, so from this intuition, we propose the syntax for conditional folding scheme by having the three algorithm. Actually, it's the algorithm C setup and the protocol fold and protocol rule. So in this syntax, the setup algorithm just returns some public parameter we denote in sort by BB, and for the protocol fold, when we fold two instance Z0, Z1 with respect to W0, W1, and some auxiliary witness W prime, then it returns a new for the instance ZW. So it's match our requirement here, and the W prime here is the supported witness for the condition. And finally, when you fold two things together to achieve the new instance, if you can prove that ZW here, you can run the rule algorithm to imply that the folding instance is satisfied. This means that the proving algorithm here can be things like some proofs that return 0 or 1 to indicate whether the folding instance is satisfied or not. So the security requirement for our scheme include three things. The first one is completeness. This means that the first one is that if the two original instance satisfy and the condition also satisfy, then the folding instance also satisfy. So here we assume that the prover and the verifier in our protocol they are both honest. The second property, soundness. In this case, we assume if the folding instance holds, if the folding instance is satisfy the relation R, then it's implied with some probability that the two original instance satisfy and the condition also satisfy. This condition here is understood to be the condition between Z0 and Z1 here. And the additional property is the honest verifier zero knowledge property. In this case, this property just protect the original witness, the witness for condition, and the folding witness. Okay, so next. So now I present the generic construction of our notion conditional folding scheme. So so to present the generic construction of our conditional folding scheme, we recall the notion of nova folding. So in this case, nova folding from KST 22 in crypto. So in this paper, they present a new relaxed R1CS constraint. So R1CS here is mean the rank 1 constraint system, and in this paper they relax this constraint system so that in this system there are three public matrices A, B, and C, and we slightly modify the witness in the system so that the witness in this relaxed R1CS has the following things. The first one is the unit element or the public element of the rank 1 constraint, and then we have the witness split into C vectors from Z1 to ZC, and we have some additional error vector. So we say that this tuple vectors satisfy the relaxed R1CS with structure S here, S equal to ABC here, if and only if A times the matrix A times Z here. This is the entry-wise multiplication. Multiply with B times Z. It should be equal to U times C times Z here, and E plus some error E. So the vector Z we use here is the concatenation of Z1 to ZC that I introduced here. So this is the notion of relaxed R1CS introduced in Nova paper, and in this way we would like to commit this tuple. So usually we employ the committed version of this tuple. This means that the public values, including U and some public information, they are public information, so we don't try to commit. But for other part of this tuple, including from Z1 to ZC and the error E here, we commit all of them, and hence we price the committed version of this tuple S to be this form. And we give a notation that if this committed tuple S here satisfies some relation R1CS here, then we understand that the witness S inside this one also satisfy the relaxed R1CS with some structures S here equal to ABC as introduced above. Okay, so next. So with this relaxed R1CS, I recall the Nova folding. So in the Nova folding, we are given two instances, S1 and S0 and S1. So here we have two instances, S0 and S1. So I denote by small I here to indicate the two instances. And after folding, after running Nova folding, we obtain the new instance S here, such that on the things here, they are the folding instance of the above two things. So in the Nova folding, they have some computation of some garbage G. This G we call it the garbage term. So in this garbage term, this is computed by the prover, and based on this garbage term, the prover commit to it, and in this case, the verifier sample and send a random channel alpha. So by using this channel alpha, property can compute the combined instance by folding by obtain SU here from SIU. This means SU from S0 and S1 together with some alpha in between. And next, the prover also obtain S dot the public instance here from alpha also, and he also combine the SZI for on I and Z. This means the things. He combine the thing by alpha, and he achieved the ZI. This means the term in the for the instance, and he also modify the error term from the first instance, the second instance, together with some garbage term here by matching with alpha. So only thing here is we the author just use some random linear combination, where the combination is based on the channel alpha from the verifier. And then after these things here, he achieved this one, these things, and these things. So finally, he obtained the final instance of S here. So next, now from the Nova folding I just present, now I present the intuition and the construction for my for our generic construction of CF scheme, our new proposed notion. So regarding the intuition, we use the previous technique from accumulation and folding technique from the previous paper, including Nova and accumulators in previous paper. Then I discuss something about the challenge. So like previous, we have Nova folding. I mean this one, the Nova folding is this protocol here. So in this one, Nova try to fold two instance, SI, including S0 and S1 here, into the new one, S. So the observation is that there is no connection between the two instances, like I told previously. So in Nova, when they use this one to construct the incremental verifiable computation, they try to delegate this one to the checkup condition into another curve, into new curves. Sorry. So because they try to move into new curves here, they need to do something like using the RO heuristic. It means a random oracle, a model random oracle as a circle, and they try to make everything into another curve. So therefore, if we would like to move out of the context of recursion heuristic and just deal with one curve and no jumping into the new curve, we need to form an additional constraint here. So in our intuition, we use an accumulator here. This is that we design a new tuple that contains a new tuple Z here that contains an accumulator S star. So these accumulators play a role of accumulating the condition, accumulating the condition. So in this case, the Z also have the original instance, and we also have the two other components, input and output. So this component input, it contains something that that is the input to the, for example, in the Rambo RAM, like we have a step, right? So the input is something before the current step. So this is the current step. So this is the input, and this is the output. So I split this one into, the first one is the main part, the input, the output, and then here we have the accumulator for the condition, and then we have some additional component including S and A here. So S A here is to accumulate some linear constraint. The first one is to compute some linear constraint, and second thing is for accumulating. Okay, so by this structure, this is the purpose for designing this structure, because when we fold by Nova, we just only fold the first things. But if we fold the first thing, then the input and output is not correct anymore. So therefore, we extract the input and the output into two other independent components. And hence, later on, when we fold things together, we can use this accumulator to accumulate the input and output and their constraint. I mean the satisfaction of their constraint together. And in other problem, we still need to make sure the linear constraint and the linear constraint to satisfy. And we use A here is to accumulate in order to extract later with respect to this linear constraints. So from this design, then we would like specifically we would like to fold that two instance in Z0 and Z1 that had the structure I just discussed, and we folded two things together to obtain the new folded instance here, Z. That have the similar structure like this. And here we would like to capture the condition between them by having this relation. So con here is for condition and G and G here is for generic. So this this is to capture the condition between the two instances Z0 and Z1. So when folding together, the first two things together into the second things, then if the second thing satisfies this relation, then the condition held, and the first instance, the second instance also satisfy those respective relations. Okay, so so now we have the design and the purpose of folding, and then I explain how to fold this one. So first, oh, I'm sorry, this one is the fold nova. This is the B nova folding. R1CS fold. So in our design, S0 and S1 they follow the original nova folding, and we have additional witness factor W here, and when folding the condition, we found the three things. The first one is the accumulator of each instant, S0 star and S1 star. And the second thing is that we form the condition between these three things together, and we found them with the output of the first step and the input of the second step. So we have two instances, right? So we have let me write more specifically. So we have two instances, S0 and S1. So we have the input I0, we have the output O0, and then we have the input I1, and we have the output R1. So here, between R0 and R1, I set a poll. Sorry, I said previously, between O0 and I1, it means the output of the first step and the input of the second step. Then it satisfies some condition. So we have some additional witness W here. So so from these three things, we form the new triple, and this triple is also a kind of relaxed R1CS triple. Relaxed R1CS triple. It means the rest R1CS instant. So we have the first instant, the commitment of first instant, the commitment of the second instant to be the accumulators, and we have the third instant to be the combination of these things, and we fold them together into the new S star. So to fold like this, we first fold the first two instants first to obtain the 40 instant, and then secondly we fold on the three together on the 40 instant, and then we continue to fold the second thing together. So we fold two times for this one to obtain the condition, the accumulator for the condition S star. Okay, so this is the idea for folding the condition. So for the remaining things, okay, so you already fold S0, S1 into S1, S star by using O0 and in1. So the remaining thing, we have I0 and O1. They are the input and output of 40 instant. So here we have the two 40 instant, the two to be 40 instant here, and you fall into a new instant. So I0 here and I1 here, I0 here and O1 here, they are the input and the output for the instant. So I set the input to be I0 and the output to be O1. And for other constraint, like I said, we still need to have some additional linear constraints. So I set S equal to S0 plus S1, and we need to be able to extract. So I use I0 and I1, and we continue to fold I0 and I1 together with some relationship here, so that later we can extract back. This means we can extract from. This means if we have this S0 and S1 together with S equal to the sum, then we can extract back S0, S1. So this is for the purpose of knowledge soundness and extraction. So I don't discuss too much in detail. It's my math loss. So I just assume that the additional instant A here, the additional component A here is for extracting in knowledge soundness, improving knowledge soundness. So from now, I already finished the folding process of our conditional folding scheme. So when we have this folding of the two instance, then for a long string, for example, for a long string of steps like S1, S1, S2, up to some Sn, then we just fold them like a binary tree. Sorry, I don't have much space. So for example, like we have the step 1, the step 2, up to the step n here. So the idea is just to fold them into a like a structure binary tree. So because of this structure, into the structure binary tree, then at the end we have a folding instance here. So in this folding instance, we can make a proof. So so because we use this structure binary tree, then we can parallelize our construction. It means, for example, we can do two things at the same time if we have multiple threads in the machine. Okay, so that's the idea of our generic conditional folding scheme. And then now I move to the next part. So from generic construction of our conditional folding scheme, then now I would like to discuss how it extends to construct RAMenPaSTA. It means it's a zero knowledge group, or we can think like a zero knowledge argument for RAM, and it achieves some property like parallelizable, scalable, and transparent. So like I said above, because we fold by the binary tree, then we can make it parallelizable, and we notice that our construction is generic. So it means that it's in natively parallelizable. It means whenever we put some proof technique or assumption into, it still be parallelizable. And for scalable, so if you so for example, if you already have a computation step like this, and then we have another step, for example, they are the 3 steps of a RAM, and another 2 steps of RAM. Then after you fold into the new one like this, then you can continue to fold. So it means you can extend them. You can extend the construction into more instance. So into more other arguments. So it's here we say it's scalable and transparent. So because we are generic, our construction is generic. So if we instantiate it by some transparent assumption, then the resulting construction is also transparent. Okay, so with this name, now I discuss into detail about the structure of a RAM. So in the RAM, we have an instruction set F, and this instruction set, you can think like in our machine, like it can be S sub moon or something. So you may notice these things, they are of course in something like Ethereum virtual machine, and like zkVMs. And we also have a register of constant number of address. So in this one, we can think like they just keep a few instance, a few space of memory, so that we can plug directly into the instruction in the first step. Then we also have the memory. So this one is extremely huge. For example, in Ethereum virtual machine, I said EVM. In EVM, the memory you can think like the memory, the storage, and the stack in EVM here. And we also have the RAM counter. So how it run, how this RAM run. So at the beginning, right, we have the initial component, including the first RAM counter, the register, the index, some domain index, some value, and some memory access. Okay, so based on this RAM counter here, we can look up from the instruction set the next instruction, look up next instruction. that instruction by computing the FBC0, FRAM BC0. So based on this net instruction, you can run the input. You can run on the inputs like the including the right register, the index of memory access and the memory access to return for the component for the next step. For example, after you running the first things, then it return like BC1, register 1, L1, 1, value 1, and memory of asset 1. So the instruction, so like I told you, the instruction is the program counter is to select the instruction, and then from the instruction it receives the input and return the new output, and it's continue to repeat this one until the step end. So here I told I already discussed about the thing, but this is not explained so far. So the triple here is, we call it the memory access triple, so that the final component is the memory operation. So in this memory operation, we have the two things. It has two values, either read or write. In the case of write, it set the memory at the index li to be equal to the value I. So index li here is li here. And the second thing is that if the memory operation is read, then it set the value 1i to be equal to the memory at the index li. Okay. So this is how the RAM works. It's based on BC to select the instruction for executing, and it's based on these things, li, 1i, and memory operation I, to access to the memory, either read or write. Okay, so now we would like to construct a zkV for RAM. So this is the short name. So it's in more general, we would like to construct a RAMenPaSTA. So our task is, first we need to prove that we correctly deselect the instruction from the instruction set. This means the instruction at step I is selected by using the BC of previous step, the program counter of previous step, and we select the FRAM BC I-1 from the instruction set here. And after we select correctly FI, then we need to prove that we execute correctly its instruction FI. And finally, we need to prove that we have the memory access consistent. So what's the memory consistency? In such a case, so for a memory, right, we have a memory mem equal to mem1 up to some mem m. This means we have a memory access. Then for example, at some address like mem_i, if you write some value v, if you write down some value v, then the next time when you read from this one, it should be also v, and you cannot change it to some v prime. So here, that's why we call it the memory consistency. So because we are using the folding scheme, conditional folding scheme, so we try to push on these tasks into the context of conditional folding scheme here. So our initial solution, our proposed solution is, first we try to realize its instruction in the instruction set by the plan structure. So I will discuss more detail about how we realize this one in plan structure. And in every step, we need to correct. So in this way, after we realize by plan structure, then in every step, we need to do two things. The first one is that we need to look up instruction. So equivalently, we try to look up the plan structure according to the previous program counter. And then after we have the plan structure, then we can do the correct execution at step I. So we should mark that FI private because we are proving in zkV. So the previous program counter is private, so we can make mi private too. We should make mi private too. And regarding, so this one is for execution. And regarding memory, we use the memory technique from the memory checking technique from previous paper, previous result here. Okay, so now I will discuss in more detail about the three things I just discussed. The first one is the lookup the plan structure. The second thing is proving the execution of the plan. And then the last one is to prove the memory consistency. And only things we try to put into the context of conditional folding scheme. So I recall the plan. The original plan paper, I try to realize every instruction, every circuit see here by the following two components. The first one is the same selectors, and the second thing is a unique permutation for the circuit C here. Sorry, this permutation is not unique. It can be some permutation that guarantee the connection of the wire. So regarding the selectors, their purpose is to try to ensure that the computation of every gate in the circuit is correct. And secondly, for the permutation, it ensures that the circuit is computed correctly throughout the wires. This means they can try to connect the wires, like input and output must match together. So by using this plan structure, we can encode every instruction in the instruction set here into the form of plan structure. So this plan structures, it contains this one is what we denote by plan structures. So sorry, so this one we denote by the plan structure is in this one it contains the permutation and the selector of the corresponding FZ here. And we have an additional index Z here is to make sure that this is we concatenate the plan structure with the index so that later on we can look up them. And the index here also make the everything in the instruction set unique, because we have the index different from different instruction. And this is for the instruction in the instruction set. So for instruction during the execution of our RAM, our proposed RAM, we denote by FI, and we also have we also encode them into the form of BC-1. This means we try to put the BC the program counter into this form, and the plan structure, the corresponding plan structure of this one. So by on this BC, we can make a lookup. This means that the plan structure of every instruction here belong to the set of instruction here. So in general, we are doing a lookup argument that we try to show that the instruction during execution on the plan structure must belong to the set of instruction set. So to do this one, in brief, I just talked in brief that we can apply the result from Harbaugh, because in Harbaugh we can transform this relation. We can transform the lookup relation here into the form of the sum. Into the form of this sum. So by on this sum, because we have the sum, so so that we can make it into the concept of folding easily. We can adapt every long structure I here from this one into the context of folding easily by having every of them into every instance of the conditional folding scheme. So that's just a brief discussion for proving lookup in folding. So the next one is for proving execution of instruction. So because we use plan arithmetization, so in plan we need to prove that the two things, the gate constraint the gate constraint and the copy constraint together. So from here we can construct a universal circuit that realize that take as input the plan structure together with some witness and return the correct computation of the function fi that has the corresponding blunt structure here. So the purpose of this circuit C is to guarantee the two things, the gate constraint and the copy constraint. So by this circuit C, we can encode it into the form of R1CS structure by having the structure ABC here. And because we can encode into the R1CS structure, then it's suitable for us to make into the folding scheme. So next. So the last thing is to prove the memory consistency. So for proving memory consistency, I just talked briefly that we use the constraint from the previous result, the previous for result here. In the for result, I specify the constraint for memory consistency by the following thing. So I just write more here, which I explain details. So in here, they need to guarantee a permutation here. So in this proving memory consistency, they need to guarantee this permutation. So therefore, we need to deal with this one in folding too, in conditional folding scheme too. So in this case, we also, to prove the permutation of this one and this one, we also transform into this sum library bus, and then putting everything of them into the every instance witness pair of the conditional folding scheme, so that later on we can fold and then we prove at the end. So I just discussed already the three things. The first one is the lookup instruction. The second thing is for proving execution of instruction, and the last thing is for memory consistency. So finally, I collect all of the components together in this one, and then from the components I partition them into the following smaller components from ZI1, ZI2, ZI3, ZI4, and ZI5. So the things for an execution step. So IUI is mean that the file typical is for the execution step of the RAM. So from here, I recall the committed tuple of conditional folding scheme. So in this committed tuple, we have the first the instance, the input and output with respect to this instance, and then we have the condition accumulator. We have the variable for computing the linear constraint and the support variable for extraction later. So after partitioning them, I separate them into the following things. So first, I set the input to be ZI1. It means this is the input to the computation. I set the output to be ZI2. So this is the output of the computation, and this sum is for here. So you remember that we need to take the sum of all the things so that later on we can guarantee the lookup and the permutation. So I put them into here for handling the linear constraint, and this one is for extraction. So I don't discuss in detail. And for the instance of every step, we put by using the following structure. This means on the ZI1 to ZI2, ZI3, ZI4, and ZI5, we put all of them together into SI. So here and the final thing is the component for accumulating. So I just put it some random tuple. So finally, after this setting, we obtain ZI with this component. So then at this step we just follow the generic construction to fold all of the tuple from, it means ZI, it means for I from 1 to n. 1 to n here. So we follow the generic construction to fall on the n instant here, on the n instant witness pair here, together into the final one, and we construct the proof at the last step. So finally, after doing like this, after partitioning, and then set the component like this one, and that after folding and proving, then we obtain the final thing, the RAMenPaSTA. This is the generic construction for proving in RAM in parallel, and also scalable and transparent if we use appropriate proof technique that have the transparent setup. And the folding here follow a binary tree structure. So because of this binary tree structure, then it's highly parallelizable. So so regarding the efficiency of our construction, I use the following notation. So for CK, I assume that is the commitment size, the size of the commitment of the message of K, of length K. And MZ is the length of every instant ZIZ. This one, sorry, this this one, CI1 to CI5 here. So MZ the length of them, the length of each of them for any I and any Z in 1 to 5. And we also have the length of the error term of each instant witness pair for S, and also the error term for the accumulator. So here we have the two instant, the two R1CS instant. So we have the two corresponding error. So I denote them by EI and EI prime. So we have the length of the two errors here too. And we also have the proof size of the final instant witness pair. It means when we fall by binary structure like this, or sometimes like this here. So at the final step, we need a proof. So B here is the proof size of the final proof. So in our protocol, we achieve the final thing. This communication cost for folding, and this one for the proof. 40 here, because we need to deal with the memory constraint. Sorry, we need to deal with the lookup. So it incurs some a factor of t. Okay, so so in our construction, we try to move out of the zk SNARK, and we can instantiate in different assumption. And if you see here that the folding process here only employ the homomorphic commitment scheme, and the proof is at the end. So so on the folding here, they are independent with the proof. So they just depend on the commitment scheme that we use. So now we so because of this construction, then we can instantiate this one into multiple contexts. The first one is the compressed sigma protocol. This one is the later result after bullet proof style. And we also have we also can instantiate in dual mode non-interactive witness indistinguishable. This is from cross high. And we can also instantiate in within the head technique from each side on, and or some other like designated variable zero proof from ITMac. So I just say here, this is the quicksilver variable. Okay, so so I already finished the discussion of efficiency and instantiation. So thank you. So now I think we can start a question and answer Q&A.
Thanks, Kaihan, for the presentation. I don't see any written questions on the chat. So everyone, if you have any questions, feel free to ask them. I have a few on my own, however, so I'll start with this. So you are using Plonk lookups. I was wondering if you had a look at other lookup schemes, because the research has been quite active the past few years. to instead.
Lookup here, the lookup, right?
Yes.
This one.
Yeah.
So you can you ask again the question?
Sure. Here you are talking about using Plonk lookup arguments. So lookup, I assume. I was wondering if you had a look at other lookup schemes. So for instance, logup, lasso.
I use the technique from Harbaugh. It means in Harbaugh, they would like to prove. Yes.
Yeah, no, sorry, I'm listening.
Okay. So I use the lookup from Harbaugh here. So in Harbaugh, he has the set Si, and he would like to prove that Si is the subset of Yi here. So so in this case, he transform the lookup argument into the form 1 plus S plus Si here equal to some multiplicity YZ. YMZ S plus YZ. So the purpose, so this is the Harbaugh lookup, and my purpose is that because we just look up the string instead of the single value, so we hash them into the single values, and then we apply the Harbaugh lookup at this one, and finally we obtain this sum. Actually, this is the sum.
This is the simulation. Interesting. And thanks a lot. Another question I had was about the condition that you have. So here you want to do IVC. So you basically ensure in the condition that the previous output equals the current inputs. I was wondering if you could modify, if you had flexibility in this condition and you could modify it. So for instance, imagine that we are working on a zkVM. You want to make sure you want to fold on valid transactions, but you're only going to fold. You only want to fold on actually valid transactions. So a condition could be that the current inputs are represent a valid transactions and not an invalid transactions. That's just an example among many others. But my question is, to go back to the question. Can you have anything in the condition? Is it flexible?
So your question means that, for example, in blockchain, right, you have multiple transactions and you would like to fold the verification of on transaction into a single one, right? So in fact, actually, as I understand, so for every transaction, you need to make it go through like a smart contract, right?
Yeah.
So in my viewpoint, this smart contract is a RAM. For example, like this. Actually, my construction cannot achieve to prove smart contract because it's quite strong. But we can view it as a RAM.
Yeah.
And then from this RAM, it's the when we decompose this RAM into the like something like for example EVM, right? So we have a set of step here, a small step here. Like that. So the purpose is this means I prove the correct execution of this smart contract by proving the correct execution of the C1 up step here. So if you have the other transaction like then you have another C1 up step, right, like this, right? So you can just fold them together. You fold one of them into a single thing, and then you fold the two things here together. It's still possible. So is it your point?
Yeah. Thanks a lot. The last questions I have, I don't want to take the mic for too long in case other people have questions. So here you are following Nova paper in that you are using relaxed one-sense constraints. I was wondering if you had a look, or sorry, had thoughts at CCS constraints, customizable constraint systems from Sethi, Thaler, and Wabi, which is a generalization for R1CS.
Yes, actually we have a look of that one, but I think other result already handle those things, and because my result is quite too many techniques, so I did not discuss much into CCS conference from SETI, right?
Yeah, I understand. It's just because you are using Planck structures and so on. I thought that looking at CCS could be quite interesting to have a generalizations of all constraint systems, and so there might be an easier integration of the lookup arguments and of the design overall through this arithmetization. Yeah,
yes.
Thanks a lot.
Thanks for your comments.
Let's see if anyone has questions. Okay. I guess no one has questions. Thanks a lot for this talk, Kaihan. It was very interesting. I'm part of the zkVM team, and I really want to delve much deeper in your paper, to be honest. So I'm really excited to learn some of your ideas and more of your work. Thanks a lot again for presenting today RAMenPaSTA. And thanks everyone for attending. I hope you had a good session, and see you next week.
Thanks, Rafa.